Hello everyone, welcome to ChemE-Shiksha. Welcome to the third video of this pump lecture series and the most important video for your interview. So today we'll be talking about pump characteristic curve, that is one of the most important topic in this pump lecture series. So let's talk about first of all the performance curve. So the pump performance curve, also called the characteristic curve of a centrifugal pump, graphically represent how the pump behaves under varying operating condition. So actually all the characteristic curve of pump, they are used to predict the behavior and the performance of the pump when the pump is in working condition under different flow rate, head and speed. So the pump performance curve is actually plotted between the head developed by the pump and the flow rate of the pump at a constant impeller diameter and constant speed. So this curve is essential for understanding how a centrifugal pump will perform in a system and for selecting a suitable pump for a given application. So in this graph we can see, right, that the head versus Q. This is actually the head developed by the pump versus the flow rate. So when the flow rate Q is 0, that means at the 0 discharge, we have the highest amount of head, that is the H max, which is called the shut-off head. So when the pump starts but the valve is closed, that means there is not any flow, that is Q is 0, 0 discharge. So as Q is 0, we know from the continuity equation that Q equals to A into V. So as Q is 0, so V is also 0 because A cannot be 0. So as V is 0, the head loss term, frictional head loss, HFS, is also 0 because we know that HFS is directly proportional to V square. So as the V is 0, so HFS is also 0. So that's why as there is not any head loss, so the head developed by the pump is actually the maximum. So this is called the shut-off head, the maximum head, that is the shut-off head. Now after this shut-off head, as Q increases, V is also increases because Q equals to A into V. So as V increases, HFS is directly proportional to V square. So as V increases, HFS or frictional head loss also increases. So as the loss increases, so head developed by the pump is decreasing because your loss is increasing. So that's why you can see over here that as Q is increasing in this direction, the head is decreasing. Head is decreasing. So this is the performance curve which is drawn in between head developed by the pump and the flow rate. So we get for different flow rate what is the head developed by the centrifugal pump. Now the next is the system curve of a pump. The system curve is also H versus Q curve, but this H is not head developed by the pump, it is the head requirement in the system. So the system curve plots the total dynamic head TDH required by the system on the vertical axis against the flow rate Q on the horizontal axis. It essentially tells us how much head is required in the system for different flow rate to move the fluid from one point to another point. So here also you can see that when the Q is 0 at 0 discharge, H is not 0. So we have some value of H at 0 discharge because at that point also the pump need to overcome the pressure difference between the suction and discharge. So that's why when Q is 0, that is the flow is 0, there is not any flow, then also we have certain head, that is to overcome the pressure difference between suction and discharge. After that, as Q increases, we know that Q equals to A into V. So as Q increases, V also increases. So as V increases, the head loss term HFS is also increases because HFS is directly proportional to V square. So as Q is increasing in this direction, we can see, so the HFS head loss term also increases, and that's why the head requirement in the system is increasing because your loss term is also increasing. So that's why head requirement in the system is increasing, we can see from this curve. So that is the difference between the performance curve and the system curve. I'm again telling, the performance curve tells us what is the head developed by the pump for different flow rate, and the system curve tells us what is the required head at different flow rates. Now at the point where this system curve and the performance curve intersect each other, that is the operating point. So this is the operating point where the performance curve and the system curves cut each other. That means this is the point where the head required in the system is exactly equals to the head developed by the pump. So that is the operating point. Now for this particular performance curve and system curve, this is the only possible operating point in the system. That means this is the only possible point where we can operate the pump, then only the head developed by the pump will be exactly equals to the head required by the pump, and the purpose of the pump will be solved. So if we want to change this operating point, because we may not need this amount of flow rate and this amount of head, because corresponding to this operating point we can see this is the head and this is the flow rate, but we may not require this amount of flow rate, we may require some little flow rate or some more flow rate. So this changing of the operating point can be done by changing the system curve, because we cannot change the performance curve of a pump. We can shift the system curve by changing the opening of the valve, or by changing the suction pressure of the or the discharge pressure. So if we, let's say this is the system curve corresponding to, let's say 50 or 70% valve opening. So when the valve is 70% open, at that point we have this amount of, this is a system curve. So if we increase the valve opening from 70% to, let's say 80%, then what will happen? So we know that across the control valve there will be some pressure loss or the head loss. So as we increase the opening of the valve, this pressure loss or the head loss across the control valve is actually decreases. So that means the head requirement in the system also decreases, because your head loss term is decreasing. So I am again repeating the same thing, that is, as we increase the opening of the valve, so we know that from across the valve there will be some head loss or the pressure loss. So as we increase the opening of the valve, the head loss or the pressure loss across the valve actually decreases. So the head requirement in the system also decreases. So that's why if we increase the valve opening from 70% to, let's say 80% or 90% anything, so the system curve will be moving to, let's say, this point. So this is the system curve corresponding to, let's say 80% valve opening. So similarly, from the similar concept, if we change the valve opening, let's say from 70% to 60%, that means we are throttling the valve, that we are closing the valve a little bit. So at that point the pressure loss or the head loss across the control valve will increase. So as the head loss or the pressure loss increases, so that means the head requirement in the system also increases. So now the system curve will move from this to this, let's say. So this is, let's say, for 60% valve opening. So we can see that for 70% valve opening, this was the corresponding head requirement, and for 60% valve opening, this is the head requirement. That means head requirement increases because your head loss term increases, and this is the head requirement for 80% valve opening, because as I told that across the valve pressure loss or head loss decreases because we are opening the valve. So that's why the head requirement in the system also decreases. Now this changing or the shifting of system curve can be done by changing the suction pressure or the discharge pressure, because we know the pressure or the head developed by the pump or the head required in the system is equals to the discharge pressure minus suction pressure divided by rho g. So if we increase the suction pressure, so discharge minus suction, this difference will if we increase the suction pressure, the discharge minus suction, this difference will decrease. So the increment in the suction pressure means decrement in the head requirement. So that means if we increase the discharge pressure for the same valve opening, let's say for this 70% valve opening, my system curve will now shift from this point to, so let me change the color. So this point to, let's say, this point. So this is also for 70% valve opening, but as I increase the suction pressure or maybe decrease the discharge pressure, that's why for the same valve opening also the operating point is shifted, or the system curve is shifted downwards, because the head requirement in the system decreases. So I'm again repeating this point of suction and discharge pressure. So the head requirement in the system H, let's say, is equals to discharge pressure minus suction pressure divided by rho g. So if we increase the suction pressure, then the discharge minus suction, this difference will decrease. So that means the head requirement in the system also decreases. So for the same valve opening, the head requirement is decreases, so that's why the system curve will move downwards. So this is the system curve for same 70%, let's say, valve opening, but as we let's say we have increased the suction pressure or might decrease the discharge pressure, because by decreasing the discharge pressure also head requirement in the system decreases, because head requirement equals to discharge minus suction pressure by rho g. Now this is the efficiency versus flow rate curve. So before that, let us talk about the pump efficiency. So any efficiency, remember this, that efficiency means output by input. So for pump also, pump efficiency will be equals to the output by input. So here it is WHP, that is the water horsepower divided by the brake horsepower. So what is the water horsepower? Water horsepower is the power gained by the fluid which is pumping by the pump. So it is equals to rho into Q into GH, or here it is written head into flow into specific gravity divided by 3960, and the brake horsepower or BHP is the power actually given to the fluid by the pump. So it is equals to actually omega into T shaft. So or you can write it that the water horsepower by the eta efficiency. So I am again repeating, the pump efficiency is water horsepower by brake horsepower. So water horsepower is actually the power gained by the fluid which is pumping by the pump, and the brake horsepower is the how much power you are giving to the fluid by the pump. Now this is the curve of efficiency versus flow rate. So as we increase the flow rate from a minimum zero flow rate, so the efficiency increases, and after a point of time, this is the point, after this point, that is the maximum efficiency point, the flow rate, if we increase the flow rate, efficiency also decreases. So why at this point the efficiency, so actually this efficiency curve should start from this point. There's a small mistake. So this curve should start from this point, because we know the pump efficiency WHP by BHP. So WHP equals to rho into Q into G into H. So as Q is 0, WHP is also 0. So that means eta is 0. So theoretically, the efficiency is actually 0 at 0 flow rate. So that's why this curve should start from this 0 point, and it will increase as we increasing the flow rate, and after this point, when the curve achieves the maximum efficiency point, then Q will decrease, and the operating point should be within the plus minus 5% of the maximum efficiency of the pump. So let's say this is the maximum efficiency and this is the plus minus 5% of the maximum efficiency point. So within this range, our operating point should be. Now the power consumption versus Q, the flow rate. So you can see this is the curve of power consumption versus the flow rate. So as we increase the flow rate, power consumption increases. It is a very simple logic. But the thing is, at the zero discharge, then also we have some power consumption. Why? So when we are just starting the pump, let's say the same logic, the valve is also closed, then at that point there is no flow, that is a zero discharge. But then also we need to overcome certain mechanical losses. That's why there is some power consumption at zero discharge or when Q equals to 0. Now after that, as we increase the power Q, the flow rate, V increases because Q equals to A into V. So as Q increases, V increases, and as V increases, HFS, the head loss term, also increases. So that's why power consumption also increases. Now at this point, when the power consumption is maximum or corresponding to the maximum flow rate, that head, so corresponding to this maximum flow rate, what head we will get, that is called the rundown head. So it is the head when the pump will deliver large quantity of fluid but at a lower pressure. So now after this point, if we increase the flow rate, then the motor will trip. So this is the maximum flow rate that a pump can achieve. Now the main characteristic curve, so this can be uh, defined by the affinity law. So when the wheel diameter is constant, that is d is constant, then how the pump wheel velocity is affecting the flow rate, head and power consumption, that can be given by this affinity law, that is q is proportional to n, h is proportional to n square and p is proportional to n cube. Similarly, when this n is constant, the wheel velocity n is constant, how the implied diameter d is affecting the all these three thing, that is q flow rate is proportional to d, h head is proportional to d square, and p the power consumption is proportional to d cube. So these are the curve of main characteristic curve, that p is proportional to n cube, h is proportional to n square, and q is proportional to n. Now there is one more thing, that is when we are changing the diameter or changing the wheel velocity, how our eta is affecting. So let's say this is the curve of eta versus q. So we know that it will start from this 0 point. This is a 0 point. So it will start from this point and let it will go up to this. So let's say this is for a particular d, when our, let's say, the diameter, the impeller diameter is, let's say, 4 inch or 6 inch, anything, 4 inch, let's say. So for 4 inch, this is the efficiency. So let's say we want 90% efficiency. So corresponding to this 90% efficiency, we have this flow rate, this and this. So that means if we want our pump to act within or more than 90%, at or more than 90%, we have to keep the flow rate in this range, right? Now if we increase the diameter, keeping the wheel velocity n constant, so we know if we increase the diameter, the head or the q is also increases, head also increases. So that's why the efficiency curve will go, again it will start from this 0 point. Now it will go like this. So let's say this is for 6 inch impeller diameter, but see over here that in this case for 90% efficiency, the range of q, the flow rate, it is actually increases from this to this. So this is my new range. So now if we want to keep more than 90% efficiency, then we can keep this flow rate from this point to this point. So for different impeller diameter, if we draw these curves keeping the wheel velocity constant in constant, and then if we add this point of the same efficiency for, I mean the for same efficiency for the q point, these points if we add, then we will get this kind of a graph like this. So let's say this is for our 90% efficiency, this is for 80% efficiency, and this is for 70% efficiency. So this kind of curve you will get. So I hope you understand all these curves. If you like this video, hit the like button and subscribe my channel. Share this video with all of your friends and be a part of a growing network of future ready chemical engineers. If you have any doubt at any point of time in this video, please feel free to ask the doubt in the comment section. So thank you for watching this video. See you in the next video.